This is the new article that we are going to discuss today, which is it is differentiation of vectors with respect to scalar. Remember, actually we are using this type of differentiation of vector with respect to scalar several times, but we have not mentioned there earlier that we are taking differentiation of vector with respect to scalar. Since this particular chapter is related to vector algebra and analysis, here we have to define very clearly, specifically, what is the process of differentiation of vector. So provided a vector is function of another scalar, then this type of differentiation of vector with respect to scalar can be taken. Similarly, if a vector is function of more than two independent scalar variables, then there comes a concept of the partial differentiation of vector with respect to scalar also. That also we are going to discuss in brief. And as you know, we have seen one derivation in the chapter number 1, that is the complex numbers, that we have calculated these components of velocity and acceleration in terms of using this complex formulation or using the complex number methods. So similar type of derivation also here can be done using this type of differentiation of vector with respect to scalar, but this time we are using r theta coordinate system or the spherical polar coordinate system rather than the xyz coordinate system. So that type of small derivations are there. We'll see one by one as follows. Now in physics we have defined several many times, many times, that is a force. So force is defined. This force is given by rate of change of momentum. Okay, rate of change, that is what Newton's second law of motion. Rate of change of momentum is called as the force. There can be several other relations there given. Here this quantity P bar is a momentum, and this is a vector. Okay, it's a vector quantity, whereas small t is time, and this is a scalar quantity. So this is differentiation of vector with respect to scalar, and the rate of change of momentum is nothing but force. So force capital F is given by dp bar upon dt. So this is the differentiation of vector with respect to scalar. Okay, now to define, this is one simple example. Based upon that, we are now writing mathematical definition of differentiation of vector with respect to scalar. Okay, so write in brief, let v bar, okay, v bar be any vector, be a vector, v bar be a vector which undergoes a continuous change in magnitude and direction. So v bar undergoes a continuous change in magnitude and direction, and is a function of scalar variable some t, small t. Don't call it to be time at present, but this is some scalar variable t. V bar is a vector which is changing continuously in magnitude and direction and is a function of small t. Okay, then the small t changes to t plus delta t, and therefore v bar will change to v bar plus delta v bar. So t changes to t plus delta t, and because of that v bar changes to v bar plus delta v bar. Okay, where this delta v bar is small increment. Okay, we are writing definition, that's why small increment in v bar corresponding to delta t in small t. Okay, change delta t in small t. So t changes by small delta t, and with that, because of that, v changes to V bar plus delta V bar. So that delta V bar is the small increment in V because of the corresponding increment delta T in T. Then the ratio delta V bar upon delta T is the average rate of change of V bar, average rate of change of V bar with respect to small t, vector variable, scalar variable. In that sense we are using these words. Okay, now as delta t approaches 0, becomes smaller and smaller, the ratio attains, okay, ratio mentioned above, that is delta V bar upon delta t, ratio attains a limiting value. This ratio becomes a constant or attains a limiting value, which is rate of increase of V bar, rate of increase of V bar. Thus it is defined as, now this is ratio, when it attains a limiting value, it is given by dV bar upon dt is equal to limit delta t made as small as possible, this ratio delta V bar upon delta t. So limit delta t tends to 0, delta V bar upon delta t. Okay, so this is what the above derivative, or this is called as the ratio of vector to scalar. This quantity, okay, dV bar upon dt is called differentiation of vector. With respect to scalar. Remember, this V bar, this is a division of vector by scalar, and therefore vector divided by scalar is also going to be a vector quantity. That means differentiation of vector with respect to scalar is also a vector quantity, or we can write here this quantity dV by is called as differentiation of vector V bar with respect to scalar, and it is also a vector quantity. This is also a vector quantity, and now I can give several examples. Or before that, let V bar is equal to, this is IVX plus JVY plus KVZ. This is my V bar in Cartesian coordinates, and here I take Vx, Vy and Vz are components of V bar along x, y and z direction, and Ijk are the unit vectors which are fixed or which are having same magnitude and direction along this x direction, unit magnitude and direction along this x direction, y direction and z direction respectively. These are called as unit vectors. Therefore I can get here, therefore if I go for this calculation dV bar upon dt here, this calculation gives me I cap as it is into dvx upon dt plus j cap into dvy upon dt plus k cap into dvz upon dt. See, these are simple differentiation of dvx with respect to t, dvy with respect to t and dvz with respect to z, and these are the rate of change of vx with respect to t, with vy with respect to t and vz with respect to z, dt again, not z. And here this I, j, k, they give me the direction and this gives me the rate of change. So this total rate of change of v bar with respect to t of a vector v bar in Cartesian coordinate is given by this simple calculation. So that is shown by this. Now some examples. There are several examples, hundreds of examples can be given, but We'll see some very simple and known example to us. We have already used this several times. First, now velocity v bar. Okay, now this is small v bar is given by dr bar upon dt, where r bar is displacement and small t is time. So velocity vector is obtained by taking differentiation of vector r bar with respect to time. So this is also differentiation of vector with respect to scalar, that is velocity v bar. Then second, acceleration, this is a bar is given by dv bar upon dt. So v bar just now obtained here, and this can be obtained as d by dt of this v bar is nothing but dr bar upon dt. Therefore this can be as second order differentiation, d square r bar upon dt square. So this is second order differentiation of displacement with respect to time. So d square r bar upon dt square is again differentiation of vector with respect to scalar, differentiation of vector velocity vector with respect to time, that gives me acceleration, and finally this expression is going to be d square r bar upon dt square. Okay, these are very common and simple examples we have used earlier several times. Then angular velocity defined by w bar is given by d theta bar upon dt. So here also theta bar is angular displacement and small t is nothing but time. Okay, these are very common simple examples. We have used several derivations earlier. Then fourth, angular acceleration, usually alpha bar, alpha is later used for that. Alpha bar is given by rate of change of angular velocity with respect to time. So d omega bar upon dt is called as angular acceleration. This is a vector. Then fifth example, as I said earlier, force, f bar is rate of change of momentum with respect to time. So this is also another very common example where force is obtained by taking differentiation of vector quantity, that is momentum, with respect to time, and that's why force is also vector and it is defined this particular way. Okay, and there can be several other examples can be given. Now we can go for some other properties. Let's take some properties of this. So if I go asked to calculate d by dt of this vector a bar plus b bar. So there are two vectors a bar plus b bar. Their addition, whatever way you use you may use for addition, the resultant quantity is going to be vector. So its differentiation with respect to scalar can be taken. And this, if I use this particular simple rule here, I can go for dA bar upon dt plus dB bar upon dt. Okay, so this differentiation is distributive. Vector differentiation is distributive. So we can distribute this. A d by dt of a bar plus b bar can be written as dA bar upon dt plus dB bar upon dt. So either you can calculate this or this, you will get same quantity. So differentiation is said to be distributive. Second, if I go for differentiation of the product a bar dot b bar, so dot product of two vectors a bar dot b bar is going to be a scalar quantity. So this is simple a scalar differentiation with respect to another scalar quantity here. But if I go for solving this, and you'll get this to be dA bar upon dt times dot b bar plus a bar dot this is d bar upon dt. This is also allowed here. So you either go by this way or this way, we are going to get the same quantity. So here d by dt of dot product of a bar dot b bar is given by dA bar upon dt dot b bar plus a bar dot db bar upon dt. There is no need to prove all these quantities. that is not necessary here. Third one is different. This is d by dt of, now this time it is cross product of two vectors, a bar cross b bar, and here this also can be written as dA bar upon dt cross b bar plus a bar cross db bar upon dt. Here, as I said earlier, this a bar cross b bar is not equal to b bar cross a bar. Therefore, if I change this order is very important, and therefore this is doesn't obey commutative law. You can write here, this vector differentiation of cross product of two vectors does not obey commutation rule. Commutation rule means order is very important. If you are changing orders, this rule gets changed. That's why we are not needed to go for this. And same thing can be given for this type of vector differentiation, can be applied for the vector triple product as well as scalar triple product, but that is not needed. We are going to discuss all these things later on when we go for actual gradient, divergence and curl and all these things there. Okay, and now once we understood this concept of differentiation of vector with respect to scalars, now let's go to the partial differentiation of vector. Partial differentiation of vectors with respect to scalar. Partial differentiation of vector with respect to scalar. Okay, so let this v bar is a function of three independent scalar variables x, y and z. V bar is a function of three independent variables x, y, z. Then, okay, this is what very simple. Already we have used this several times, so I'm just repeating this. The partial derivative of v bar with respect to x is given by, okay, we calculate this, or we know all this. This is continuous, we do not know this. It is partial differentiation of v bar with respect to x is equal to, if you remember this, limit delta x tends to 0. Now v bar of change variable x plus delta x and y and z as it is, minus v bar of x, y and z. So x changes from x to x plus delta x, therefore v changes from v to v plus delta v, and therefore delta v upon delta x is given by this limit, this new variable, a new change or the change value of v, original value of v, divided by this delta x. So this is defined as the partial derivative of delta v bar upon delta x. Similarly, delta v bar upon delta y and delta v bar upon delta z are also defined. No need to write this, but I can write this: v bar of x and y plus delta y and z minus v bar of x, y, z upon delta y in the limit delta y tends to 0, that is called as delta v bar upon delta y. That is partial derivative of v bar with respect to y. And similarly we can define partial differentiation v bar with respect to z. Okay, this is what a partial differentiation. And here in the first case we have consider only x changes and y and z remain constant, or y changes, x and z remain constant, or z remains constant, z changes and x and y remains constant. So accordingly we can get partial derivatives. Now if all these three variables, if x, y and z change simultaneously, at the same time all are changing by differential elements, differential increments, not elements, increments, respectively dx, dy and dz, then what we get is called as total differential. Then the total differential of v bar, total differential of v bar is, okay, we have already used this method. So dv bar is equal to, it is partial differentiation of v bar with respect to x multiplied by dx plus partial differentiation of v bar with respect to y multiplied by dy plus partial differentiation of v bar with respect to z multiplied by dz. So remember, in this case also what we have done, we have taken differentiation of vector with respect to scalar. So dv bar is equal to, total differential dv bar is equal to partial differentiation of v bar with respect to x multiplied by dx, partial differentiation of v bar with respect to y multiplied by dy plus partial differentiation of v bar with respect to z multiplied by dz. Earlier in chapter 2 we have done everything of this. There we have not mentioned this is a differentiation of vector with respect to scalar, but here in this chapter we are taking quantity in the numerator is a vector physical quantity, therefore, and quantity in the denominator is the scalar physical quantity, therefore this becomes a differentiation of vector with respect to scalar. So the laws of differentiation what we used in earlier chapter number 2, same laws are applied here, only notations are to be small change. Okay, this is called as partial differentiations and this total differential. Now higher ordered derivatives are also defined. Higher order derivatives are also defined, and you might be knowing all this. So I can go for this. First differentiation is dabba square capital V bar upon dabba x square. Okay, so an example I can write this is dabba by dabba x of dabba v bar upon dabba x. So this is again differentiation of variable v bar with respect to x, and then this is a vector quantity which is differentiated again with respect to x, and that gives me dabba square v bar upon dabba x square. So this is second order differentiation of vector with respect to scalar x. Second, I can go for this dabba square v bar upon dabba x dabba y, cross multiplication or mixed partial differentiation. So this is nothing but dabba by dabba x of dabba v bar upon dabba y. So first take differential of vector v bar with respect to y. This is again a differential of vector with respect to scalar. So this is going to be a vector quantity, and then differentiate with respect to x. We will get dabba square v bar upon dabba x and dabba y. And also here also in general, dabba square v bar upon dabba x into dabba y is equal to dabba square v bar upon dabba y dabba x. Okay, that is if order of differentiation is also changed, usually we get this to be same or this to be similar. Okay, so here also this rate of change of v bar with respect to x, rate of change of v bar with respect to y, rate of change of v bar with respect to z. Okay, we have not done this thing here, but this is also a differentiation of vector with respect to scalar. Okay, now this is one small theoretical aspect we have covered. Now let's go for calculating. How much time is there? 10 more minutes are there, so we'll just try to finish this derivation. So give a next title, components of linear velocity. Components of linear velocity and acceleration. Acceleration in plane polar coordinates. Plane polar coordinates. And why we are needed to this? Sometimes in physics, solving problems using systems, coordinate systems other than Cartesian coordinate system is bit easier or simple, or that is a more technical, more good. So what is that? This is what, whenever we are supposed to go for a circular motion or motion of earth around moon, moon around earth, as well as motion of earth around sun, or any circular motion, it is very easy to use polar coordinates rather than this xyz or Cartesian coordinates. So therefore we have to go for this simple diagram. First draw this diagram, and then we will understand how these things are to be discussed. Okay, so this is my x y. Okay, I am taking two dimensional. This is x coordinate and this is y coordinate, and here this point P is located. This is my point P, and this is my origin 0 0. So we can draw a vector from this to this. This is called as position vector. Okay, and this is my r bar. This is point P. Okay, and the angle made by this vector with this is going to be theta. So r bar and theta, or these are the two different coordinates, and as I know here, this in this direction of x axis, this I cap is the unit vector. In the direction of y axis, there is a unit vector. This is said to be j cap, and here I can take this intercept from this point to here. I'll get this point. Here to here, if it is taken, I'll get this point here. So this is nothing but my value of x, okay, and this is value of y. Now look here, I have to use this transformation equations. I'm using, this is xy is Cartesian coordinate system, and here in the same coordinate system I am using location of this point P. Can be represented by P has coordinates x and y, and P also has coordinates r and theta. So r is given by this length of the position vector from origin to that particular point, and the angle made by this vector with direction of x axis is going to be another coordinate, that is theta. So P point can be expressed by these two coordinates x, y in Cartesian, and in polar coordinates it is represented by this point r theta, or coordinates r and theta. This is what here. Now we know the relations between coordinates in two system. This is also a repetition. We have done it earlier, but since again we are doing this. Now x can be calculated as, so how x can be see, cos theta is equal to x upon this r bar, isn't it? So cos theta is equal to x upon r bar, therefore x is equal to r times cos theta. I am writing scalar relationship, and y is given by r times sin theta. So use this right angle triangle here. This is right angle. So here I can use sin theta is equal to this side y upon r. Therefore sin theta is y is equal to r sin theta, and x is equal to r cos theta. And inverse transformations are also known to you. Using this I can write x square plus y square will be r square cos square theta plus r square sin square theta, and therefore r square into the bracket sin square theta plus cos square theta is 1. Therefore I'll get r square is equal to x square plus y square, and therefore r is equal to root of x square plus y square, and take ratio of these two, y upon x, that gives you r sin theta upon r cos theta is equal to tan theta is equal to y upon x, and therefore I can write theta is equal to tan inverse of y upon x. In chapter 1 we have used all these things several times, so we are not going to discuss anything about this. So this is what, these are the two coordinate systems, xy, that is Cartesian coordinate system, and r theta, that is the polar coordinate system. And now here I have to draw unit vectors in the direction of, okay, so draw this vector here. This is given to be er cap. So this is called as unit vector in the direction of increasing r, and see theta increases in this direction. So I have to draw a perpendicular vector here, which is shown at this point, which is given to be e theta cap. So this er cap and e theta cap are called as unit vectors in the polar coordinates. We have to get relations for that. त्याची relations apply मिळवायचे. But before that I know that I cap and j cap are the unit vectors in the Cartesian coordinate. Likewise, so I cap represents the direction of increasing x, its magnitude is 1. J cap gives you direction of increasing y, its magnitude is also 1. So this is why these are called as unit vectors. Here I cap and j cap are perpendicular to each other, therefore two-dimensional Cartesian coordinate system is orthogonal. We have tried this also, and here also we are showing that er cap and e theta cap are two unit vectors in the direction of increasing r and increasing theta respectively.
they are drawn in such a manner, they are also found to be perpendicular. Therefore this system is also said to be this is also said to be a orthogonal coordinate system. Okay, so but here we are just going to define one thing and then we'll stop because our time is going ahead. So let's just write here. Now let's hear these relations what we have written here, these equations. Okay, call this to be equation 1. Both of this is equation 1. These are transformation equations or transformation equations from system 1 to system 2 and all that. This is known to us. Now let's write here in brief. If r bar is the position vector, of a particle at time instant t, small t, making an angle theta with x-axis. Okay, then now this is very important thing here. I am writing dabba r bar upon dabba r. What is this? आता पहा या ठिकाणी खरं तर r आणि न्यूमरेटर मध्ये डिनॉमिनेटर मध्ये पण r आहे, but this is not that simple. R bar is vector r bar and small r is the our coordinate, small scalar coordinate. This is r. So this is again differentiation of vector with respect to scalar. The quantity defined as dabba r bar upon dabba r is a vector in the direction of, this is the definition, in the direction of increasing r bar. Okay, now let's what we are writing. आपण काय म्हणतोय पहा, I am calling, okay, r bar is my previous vector आणि rate of change of r bar with respect to length r, that is called as the vector in the direction of increasing r bar. Okay, hence आणि मग आपण लिहू शकतो hence a unit vector in the direction of increasing r, okay, increasing r bar is given by okay, er cap is equal to the vector itself, that is dabba r bar upon dabba r divided by its magnitude dabba r bar upon dabba r. This is my first unit vector. Call this to be relation number 2. So er cap, unit vector in the direction of r bar, is defined by this dabba r bar upon dabba r. R bar is a vector, r is the coordinate of the system, polar coordinate system. So first coordinate is r, therefore differentiation of vector with first coordinate is taken. So this is a vector, differentiation of vector with respect to scalar. It's a vector quantity, its magnitude can be calculated in the denominator, and if it is divided by this vector, I'll get unit vector in the direction of r, that is given by er. Similarly another vector e theta cap is given by, this is vector dabba r bar with respect to theta, differentiation of vector with respect to another scalar, that is theta, divided by its magnitude dabba r bar upon dabba theta. Call this to be 3. Okay, so see in this diagram, in the next lecture we have to repeat these things again. So I am given xy coordinate system. In that case, a point P is denoted by or specified by two coordinates P of xy. Now here also I can use the point P can be located by another coordinate system by that is where r and theta are the two coordinates, that is plane polar coordinate system. So here r and theta are the variables. Therefore r bar is defined as the position vector of this point P from the origin. This is a vector, angle made by this vector with this x-axis taken to be theta. Then from this diagram I know the relationship between the coordinates for the xy coordinate system or Cartesian coordinate system and polar coordinates as given by equation 1.
and if it is known, we can go for differentiation of vector r bar with the new coordinates r and theta, and if these vectors, these changes are obtained, and if they are divided by their magnitudes, what I am going to get is called as unit vectors in the direction of increasing r, which is given by er cap, and unit vector in the direction of theta, that is given by e theta cap. So try to understand, these are called as unit vectors for the plane polar coordinate system. Polar coordinate system, these are the unit vectors, and they are not I cap and j cap. I cap and j cap are for Cartesian, er cap and e theta cap are the polar vectors or unit vectors for the polar coordinates. Okay, so next to this are other things, that is again a lengthy derivation that will be done in the next lecture. Okay, so today we'll stop here. Thank you. Just a minute.